So we're going to continue our discussion of the definite integral. So let's recall the definition and some properties that we saw in the flipped class video. So we're going to consider some function f of x on some interval ab. We're going to set delta x to be b minus a over n. And then we'll use this to break up our interval into n equal size pieces. So we'll say x0 is a, x1 is a plus delta x, so increasing these by delta x each time, all the way until we get to the last one, which is a plus n delta x, which is the right edge of the endpoint, interval b. Now we're going to choose some xi star in xi to xi plus 1 for each I with 0 less than or equal to I less than or equal to n minus 1. So this means we're just picking a point in the interval for each subinterval where we'll be evaluating the function for our Riemann sum. And so then we have our definite integral from a to b of f of x dx is the limit as n goes to infinity. And you can use these points here. Now, when we saw in the flipped class video how, depending on how you choose those points, you can, if you want to, you can recover the left-hand sum or the right-hand sum or the midpoint sum. Or you can just pick any points you want in the interval. It doesn't have to be, could be some mix of those. So that's our definition of the definite integral. Okay, and some properties of this that were given and explained in the flipped class video are the following. If I take the definite integral of a constant times a function, I can pull that constant out front of the integral. If I have two functions and I take the definite integral of the sum of these functions, this breaks up into the sum of the definite integrals of these functions. So a definite integral breaks up over addition. If I take my definite integral, I can break this up by going to some point C in between for any C with A less than C less than B. And then finally, if I flip the order of the limits on the integral, it introduces a negative sign. So those were our properties. They should be familiar from the flipped class video already. So now let's see some examples using these properties and the definite integral. So this is my function y equals f of x. Let's say this point is at A, point is at B, and this point is at C. And we're going to say this area here is equal to, say, 8, and this area here is equal to 3. So let's see how this gives us values for some various definite integrals. So for instance, if I look at the integral from a to b of f of x dx, now from a to b the function is always positive, so that means that the definite integral just gives me the area from a to b under the curve f of x. So in that case, this is just 8. Now if I want the integral from a all the way to c of f of x dx, I know since b is between a and c, I can break this up to be the integral from a to b of f of x dx plus the integral from b to c of f of x dx. And now we just saw that first one is given by 8. And so now notice from b to c, our function is negative. So that means the definite integral on that interval from b to c is the negative of the area. So this is plus negative 3. So the answer for that one is 5. And finally, let's look at one last one here. So let's look at the integral from a to c of the absolute value of f of x dx. Now again, we can break this up from a to b, absolute value of f of x dx, plus the integral from b to c, absolute value of f of x dx. And now notice that since the function is positive on the interval from a to b, the absolute value just gives me f of x back. And on the second interval from b to c, the function is negative. So that means the absolute value is negative f of x dx. So this one is 8, and then I have minus the integral from b to c of f of x dx. And we saw that was negative 3, so this becomes 8 minus 3, which is 11. Let's look at one more example here. Let's suppose we have 0, so we have positive f of x, but it's less than some function g of x on my interval ab. So maybe this looks something like this. So let's just draw this situation out. So we'll say my function f maybe looks like this. And maybe g looks something like this. Maybe it comes up and it touches it there. It goes something like this. So that's our situation. So we can ask ourselves then, what does the integral from a to b of g of x minus f of x dx look like? Well, we know this is the same as the integral from a to b of g of x plus negative f of x dx. And then we can use our integral properties. So it's the difference of these two definite integrals. And now let's think about what each one of these is. So maybe let's color code these. So let's say this one here is given by green. So that would be the area under this curve. So that would be this part here. And then let's say we'll use pink for the other function. So this will be pink. So that's the area under G. We'll draw that in this direction. Now, since we're subtracting these, we can see what is the total then. So let's pick one more color. Go with a cyan color here. So this total thing then is the difference between these, which is this part here. So this is the area between these two functions. So this whole thing is equal to the area between f of x and g of x. So that gives a geometric interpretation to that. So we have the definition of the definite integral we're going to work one example from the definition. We'll see from working this one example that one example is more than enough, and we don't really want to be computing these things from the definition. It's quite painful even for a simple example, but it is worthwhile to see kind of the techniques that go into this, just so you've seen one example and see kind of how to work things. So let's evaluate the following integral. Okay, so this is pretty simple. We're just a degree 2 polynomial. This shouldn't be a lot of work. But when we only have the definition, it is actually quite a bit of work. So what we're going to first do is we're going to set up the right Riemann sum with n subdivisions for the function inside here. This is going to be for the function f of x being x squared plus 3x plus 1 on the interval from 0 to 2. So with the setup we've been using, our delta x here is 2 minus 0 over n. So 2 over n. And then our interval edge points, well, we're going to start with 0. x1 is 0 plus delta x. This is just 2 over n. x2 is 0 plus 2 delta x. This is 2 over n, and so on. So xj would be j times 2 over n, all the way to xn, which is n times 2 over n, which is just the right edge of the interval 2. So let's see what our right Riemann sum is then using our definition. Remember, to get the definite integral, we're going to eventually want to take the limit of this sum. So this is just our definition. So now let's plug in for our function. So this should be xi squared plus 3xi plus 1 delta x. And now we'll use what these xi's are. So xi, remember, this is I times 2 over n plus 3 times I times 2 over n plus 1. And then remember, our delta x is 2 over n. So let's simplify this as much as we can. So this first term, when I square this, I'm going to get an I squared times 4 over n squared plus 3 times, or let's write this as 6 over n times I plus 1 times 2 over n. So distributing this through, I'm going to have an I squared, and I'm going to have 8 over n cubed plus 12 over n squared times I plus 2 over n. Now we'll break this sum up, and let's bring everything that doesn't involve I out front of the sums. So I'm going to have 8 over n cubed, summation from I equals 1 to n of I squared, plus 12 over n squared, summation from I equals 1 to n of I, plus 2 over n times summation from I equals 1 to n of 1. So what we see then is, if we want to take the limit here, we don't really know how to take limits of things that look like this. So what we need to do is we need to figure out nice formulas for this, this, and this. So one of these things is not like the others and is easy to do. So if I look at this sum, this is just adding 1 to itself n times. So this is just n. So let's keep track of that. We'll box this in because we're going to come back to this later. So we're going to use this. And now we need to do the other two sums, and these ones aren't quite so obvious. These ones are going to require some tricks. They're not things you would necessarily think of, but hopefully we can follow along. And even though we might not think of these, hopefully we can understand what works here. So this is the one we're going to look at next. So what I'm going to start with is I'm going to look at 2 times this sum. So this is 2 times 1 plus 2 plus 3 plus. And so now I'm going to take that and I'm going to write it out twice. So I'm going to have 1 plus 2 plus 3 plus n minus 1 plus n. And I need another copy of this. But the trick I'm going to do is I'm just going to happen to write this in the reverse order. So I'm going to go n plus n minus 1 and all the way down, and I'll have plus 2 plus 1. And now notice if I add those and I add them up in the columns, we can evaluate each of these. So notice this is n plus 1. This one is n plus 1. All the way down to this one is n plus 1, and this one is n plus 1. So there are n copies of n plus 1 here, so this is n times n plus 1. So what we've shown is if I look at 2 times the sum from I equals 1 to n of I get n times n plus 1. So to get what I'm interested in then, I just divide both sides by 2. And that gives me my second formula that I was interested in. Okay, so we saw we had to use a little trick here to get this, but it wasn't terrible. The next one's a little bit more difficult yet. We need another trick that isn't quite so obvious of just rearranging things. So for the next one, I'm going to use another trick. So let's write down what we're trying to solve here. So we're trying to figure out this sum. Now, one thing to know is once we know how to do these sums, it would be easy. Once I know how to do this I squared one, it would be easy to integrate any polynomial of up to degree 2 now that we know these formulas. So for at least for polynomials, we just have to keep doing these tricks to get different powers, and then we'd be able to continue to do higher degree polynomials. But again, this isn't something we really want to spend a lot of time on. So let's look at the following sum. Now we're adding cubes, so it doesn't seem like this would actually be helpful. But what we can notice from this is that this has a lot of cancellation in it. So if I look at the first term, I'm going to get 2 cubed minus 1 cubed. So that's what happens when I is equal to 1. When I put I equals 2 in, I'm going to get 3 cubed minus 2 cubed. And then the next term will be 4 cubed minus 3 cubed, and so on, until we get to the last one, which is going to be n plus 1 cubed minus n cubed. And now what we want to notice is we get all of this cancellation here because this 2 cubed cancels with this 2 cubed. This 3 cubed cancels with this 3 cubed, and so on all the way up. So we see each term will cancel except for this negative 1 cubed doesn't have anything to cancel, and the n plus 1 cubed doesn't have anything to cancel. So that whole sum cancels out to be just n plus 1 cubed minus 1. And if we simplify this, this gives me n cubed plus 3n squared plus 3n. And of course, at this point, we're thinking, what does this have to do at all with this, what we're trying to find here with the I squared? Well, we can also do simplification inside the sum before we do it. So I can look at this sum in another way. If I have I plus 1 cubed minus I cubed, this is I equals 1 to n, and I'm going to have an I cubed plus 3i squared plus 3i plus 1 minus I cubed. So note we get cancellation inside this, and I get 3i squared plus 3i plus 1. And now I can break this up and pull terms out. And the important thing to note here is look at what we found. We found this term we're interested in. And we know these other terms here. And so what we can see is if we combine this calculation we did up here, so this gave me this sum as n cubed plus 3n squared plus n, and this gave me it as this. So we have, in particular, the summation from this is equal to what we calculated above, which was n cubed plus 3n squared plus 3n. So now let's solve for what we're interested in. And I'm going to bring those other two terms to the other side. And now we use the fact that we already calculated these sums above to get this. So if we want to get a common denominator, I have 2n cubed plus 6n squared plus 6n minus 3, and then distribute this out. I'm going to have n squared minus 3n minus n. Well, that's right, this needs to be a 2n because we're going to get a common denominator over 2, and this whole thing is still equal to this. Now divide through by that 3. And we can do a little simplification on the top as well while we're going. So I have a plus 3n squared, and then I have plus n all over 6. And this factor like this. And this is equal to n times n plus 1 times 2n plus 1 over 6. So if you didn't see that last factorization, of course it's a quadratic, so you could use quadratic equation to factor that. So the point is we have this last formula now. And that was the last one we needed to calculate in order to put our right Riemann sum into a nice form. So let's go back to that. So remember I had Rn was equal to 8 over n cubed times the summation from I equals 1 to n of I squared plus 12 over n squared summation from I equals 1 to n of I plus 2n times summation from I equals 1 to n of 1. So now we can fill these formulas in. So this is 8 over n cubed, and then I have n plus 1, 2n plus 1 over 6 plus 12 n squared times n plus 1 over 2 plus 2n times n. And then let's just regroup these things a bit. So if I put the 8 and the 6 together, I get a 4/3. And then I have n times n plus 1, 2n plus 1 over n cubed plus 6 times n plus 1 over n squared plus 2. So there's a nice, easy, what we call the closed form expression for a right Riemann sum. So now we're finally in a position to be able to evaluate the integral. Remember, this is the limit as n goes to infinity of this right Riemann sum. So this is the limit as n goes to infinity of 4/3. And then I can write this as n plus 1, 2n plus 1, and then just break these n's up into n times n times n, plus limit as n goes to infinity of 6 times n plus 1. And again, let's write this as n times n, and then there's no limit, so that one will just be 2. And now when we simplify this, because we want to take this limit, this 4/3 stays the same, and then just look at each and simplify each of these things on their own. So this becomes a 1. This part, if I divide that out, it becomes 1 plus 1 over n. And this last one becomes 2 plus 1 over n. And we do the same thing for the others. And then for this, I'm going to get a 1 times 1 plus 1 over n, and then plus 2. And then just note as n goes to infinity here, I get 4/3, and then I get 1 times 2, because 1 over n goes to 0 as n goes to infinity, plus 6 times 1 plus 2. And so if we simplify this, we get 32 over 3. And so that allows us to evaluate that definite integral using the definition. Though again, not a great way to do this, but it can be done. But we're going to in the future see a much, much better way to evaluate some integrals. So one thing to keep in mind, that I'm going to say this over and over, is that a lot of integrals you would encounter in calculus class are very nice integrals, and there'll be nice formulas for them. But if you're actually trying to find integrals like in the wild, so in actual real world settings, most of the time those integrals aren't going to be something that have a nice formula for them, and you're going to have to actually approximate them numerically, which we'll see how to do. We've already seen how to do it using left-hand, right-hand, and midpoint sums, and we'll see a couple of other methods as well later on.